in this video, we will be getting a visual understanding on increasing decreasing function, their relationship with the first order derivative and maxima and minima, as well as global maxima and global minima, and their relationship with first order derivative as well as second order derivative. So let us begin. So basically I have drawn a fifth degree polynomial here. We will analyze its behavior at some points. You can see there is a vector that points out each and every value of the polynomial at every coordinate. So you can definitely get intuition that something is happening here. First the function is value increases, then again decreases, and again it increases to some point and again decreases. So you can definitely get a feel that it somewhere it gets its maximum value that it can be, and it again changes its behavior. So we will see what are the conditions that actually govern this behavior of the curve. We will also see how this increasing and decreasing behavior of a particular curve is related to its first order derivative and also its second order derivative. So before going to the point of discussion, remember that when we define maxima or minimum or increasing or decreasing behavior of a curve, we basically move towards the positive part of the number line. Okay, that is, we move towards right side of this number line. Okay, so I will suggest to visualize what is happening here. Here, do have a look what is happening. You can see that at this point, the function just crossed the local minima. Basically, local minima means a point inside the interval in which the curve is defined, it gets a minimum value. But that may not be the most minimum value that it can occur. Here you can see that the least value that it gets is this value. This is the least value. This is not the least. So we will call this value the local minima. Sorry, the global minima of the curve, and this value the local minima of the curve. Like this, these two are the local maxima of the curves. Okay, to have visualize. When it goes to attain the maxima value, that is the local maxima, the slope of the curve is a positive value. And when it crosses the local maxima, you will see that the value of the tangent at that point, or the slope value at that point, will be at 0. Now you look at the cursor that I am pointing out. This is the point of the local maxima, and here the slope of the curve is 0. Also you can look at this point. Here is also the slope of the curve is 0, and this point also has the slope 0, and this point also has the same thing. So what I conclude here is that whenever some function attains at its local extrema value, then the slope of the value of the function becomes 0. Fine. And now I would like to introduce a new term. Whenever the slope of the function becomes 0 or undetermined, that point is known as a critical point. Remember this, we will come back to later. Okay. So I haven't discussed yet critical point, but I will discuss it in the subsequent videos. Right? But as of now, just remember that what is critical points, and so you can also be sure that these points of local maxima and minima are also the critical points of that curve. Okay. Here the function attains maxima, but where is the global maxima? I have discussed about local minima and global minima. It is the point of global minima, and this is the point of local minima. But where is the global maxima? So the global maxima is this point. Okay. Now you might be wondering that here the slope of the curve is definitely not 0. Then how can you consider it as a global maxima? Basically, the thing is, although this is not a critical point, but this is the global maxima of this curve in this particular interval. Okay, but if we extend for this particular curve, even if we extend that graph to beyond this, the interval that I have taken, this will never reach again the slope will never become 0. So if we extend this graph indefinitely, then it won't have a then its global maximum would not be defined. So to define the global maxima, we need to have the interval so that we can have a global maxima. So why this the slope of the curve will never become 0? This is because I have in the starting of the video defined that this polynomial is a 50-degree polynomial. So it has already crossed x-axis 5 times. You can see second time, third time, fourth, and again here. Here again it has crossed the curve. Okay, so it has already 5 roots. So it can't have another root. So that's why it won't cross x-axis again. So that is why we will not get a critical point after this interval, after this point. Okay, I mean if we extend this curve, then we will never get a critical point again. So that is why this point in this particular interval that I have taken is a global maximum. Now let us understand what is an inflection point. Basically, it is a point on the curve where the first order derivative of that curve is 0, but that point is neither a maxima nor a minima. So for this visualization, let us draw the graph of x cube. So basically, the grapher draws it. So this is basically the graph of x cube. Now look at this graph and look at the tangent also. So try to visualize and on your own try to understand which point in this curve is the point can be a point of inflection. So wait a bit, if your answer is this point, then definitely you are correct. This is actually the inflection point that we are talking about. Have a look. The 0, 0 point or the origin point for x cube graph is the inflection point, and you can always see that the slope at this point is 0, but this point is neither a minima nor a maxima. So you can also wonder that whenever the slope is 0, then that point is a critical point. So is this inflection is also a critical point? Yes, definitely, that is also a critical point. Okay, so you can also see visualization that nowhere in the curve the slope is 0. Here the slope is not 0. Here also the slope is not 0. So you can basically visualize this. Also, you know that x cube has only one solution, though it is a cubic polynomial, but it still has only one solution, because x cube is equal to y. That means all the 3 identical solutions are present in this curve, that is 0. Okay, so 3 solutions are identical for x cube. That is why we are getting only the curve crosses x axis only once. That's why. So we also got sure that this curve will never cross x axis again. Fine. So here I have again drawn the same graph where we examined the behavior of local maxima and local minima and the relationship with slope. Now I want to tell you a basic difference between what differences a point of local maxima or minima with that of a point of inflection. So here you can see that whenever we cross a point of extrema, that is a local maxima or minima, the slope changes its value. You can understand here that the slope is positive here, it crosses the local maxima and becomes negative, and same happens when it crosses the point of minima also. You can visualize this also. Yes, have a look. Yes, you can definitely visualize it. It is negative, it crosses local minima and becomes positive. Now let us analyze the same for uh, that is the slope behavior for a point of inflection. You can see that the slope doesn't changes its sign when it crosses the point of inflection. Here it is positive, it becomes 0, and again remains positive. This is the main difference between the point of inflection and a point of local minima, local maxima, or a global minima or a global maxima. Or basically, this is the main difference between a point of extremum with that of a inflection point. Okay, so that's all for today's video. So in the next video, we will look into the use of second order derivatives and their connection with whatever we studied today. Okay, so stay tuned for that, and I will request you to, if you have liked this video, if you love this video, then definitely do like it and do give the valuable comments so that we can improve. And definitely don't forget to share it with your friends so that they can be benefited in spiritual understanding. Okay, so thanks a lot.